So in the last lecture, I described the Deutsch algorithm and its generalization by Deutsch and Jozsa. I'm going to repeat it because understanding the steps is important. And before I do that, let me emphasize some general features that in general quantum algorithm, there are superpositions and because of various logic gates that produces entanglement. The consequence is that you cannot talk about individual components of the circuit being in a particular state. It's all correlated. So whatever the signal is there, the signal belongs to the circuit as a whole. You cannot break it up into components. The only place where you can break up the signal in the components is either at the start, where the initial state you assume to be factorized, or at the end after performing the measurement, because then you do projections and all the superpositions get destroyed at that particular state. But anywhere in between, even though we draw diagrams with all components and all gates, etc., the state is not separated into components. It's the state of the whole circuit. Okay, you have to keep that in mind because the classical notation is different. When you say that this particular component is there, you can identify its state. In the quantum case, you cannot.
Even if initially they are separated, the circuit does something to them by which they got integrated.
Yeah, the job of the circuit is to correlate all the components in some particular manner. If you don't do that, then you will have classical computation. You will not have any advantage coming from quantum logic. So all the advantage of quantum logic is coming because of the superposition and correlations which are absent in the classical part. So okay. So now let me repeat the circuit which I wrote down for the Deutsch problem, that we had a state 0, applied the Hadamard transformation, and then state 1, applied the Hadamard transformation, then there was a control operation which gives a phase, then another Hadamard transformation, and then there is a measurement. And nothing is done onto this other part. So all that is done in going to the Deutsch-Jozsa problem is that this input state, instead of just being 1 qubit, it's made into n qubit. So I'm just denoting by drawing a slash, which means that there are actually n qubits and it's just not 1 qubit line, but the operations are the same. So let us now step by step look at what happens. So there is a initial state which is 0 to the power n and 1. This exponent denotes how many qubits are there. So there are so many in this state and so many on 1. Then you apply this gates, which is Hadamard on each one of them and multiply by Hadamard on this, and the result of that is quite straightforward. This 0 becomes this, and the 1 becomes this, and which can be rewritten as the 0 minus 1 remains unchanged, but you expand this thing out. It is just a sum over all the 2 raised to n possibilities occurring with equal amplitude. This power is equal to this. Yeah.
Does that mean that we have generated the n qubits in 0 state and supplied the circuit?
Yeah. So this is how many terms are there? This is x equal to 0 to 2 raised to n minus 1. Because each binary representation of 0 and 1 occurs 1 in this whole tensor product, something which I have used several times before. So that takes care of the initial part. Now I apply this control UF. So what was the result I wrote down last time? It's a control depending on this x, and UF on this basically adds either 0 or 1 to this thing. If it adds 0, the state remains unchanged. If it adds 1, it changes sign. So the whole thing can be rewritten as a state which is x equal to 0 to 2 raised to n minus 1. There is x, then there is minus 1 raised to f of x, and this will remain factored out unchanged. Okay. The minus 1 raised to fx actually came from the action on this particular bit, but as I said, the state is of the circuit as a whole, and I have just grouped together all the terms which depend on x. This doesn't depend on x, though it contributed this factor minus 1 raised to f of x. So that was the result of this particular operation. Then I apply this operator over here, and nothing is happening over here, so I can write it as just identity. So it is going to operate on this x dependent part of the state. Nothing is happening to the identity, and the action of this Hadamard operator on x is again something which can be written as a phase factor, which is -1 raised to x dotted with y. There is actually a double sum. This is a binary product. So when I operate on the state x by a Hadamard operator, it produces -1 raised to x dotted with y, because only place where the minus sign is there is when both x and y coordinate are equal to 1. Otherwise it doesn't do anything. And the dot product comes because this is going to act on each of the n qubits one by one. So it is x1 y1 plus x2 y2 plus x3 y3, etc. So this is the whole algorithm, and then there is a final measurement. What will happen when I measure this n qubits? I'm not doing anything to this other part at all. So now you have to ask specific questions, that the function has only two possibilities. Either it is constant or it is balanced. That is given as a part of the problem. So if the function is constant, this doesn't matter. It goes outside the whole calculation, and this is a bunch of oscillatory terms, because sometimes x and y, they are all individually going over two values, 0 and 1, and if the two values are occurring equally well, which is the true case in this summation over all possibility of x and y, the +1 and -1 will cancel out. So the only term which survives is where the exponent doesn't oscillate between -1 and +1. And that can happen only if the exponent is 0. Okay. If y is equal to 0, whatever the value of x doesn't matter, they just all add up. And you can work out the normalization rather trivially, which I kind of lost somewhere in these steps. So there was a 2 raised to -n/2 inside here. Here it got used twice. So because of the second sum, it is actually 2 raised to -n. And now if y is equal to 0, this phase goes away. I have a sum over all x, which are exactly 2 raised to n in number. So that will cancel this factor completely, and I have only a normalized state, which is y equal to 0. Okay, so normalization is maintained. I have not lost anything in the calculation. This is an exact result. On the other hand, if the function is balanced, that means half the time this f of x is plus 1 and half the time it is minus 1. In that particular case, look at this particular term, that if I have y equal to 0, this function is absent. This one is half the time plus 1 and half the time minus 1, it will cancel out. So the result is it will produce some superposition of many different y. I am not bothered about it, but the y equal to 0 term is absent. That is the crucial point. You can work out the normalization. It will come from this 2 raised to minus n and how many of these terms are there, and some of them will have to be adding up, etc. Doesn't matter. The crucial point is it will be a superposition in which y equal to 0 term is absent. So all you do is perform this measurement. If y is equal to 0 is the answer, you know that the function is constant. If anything else shows up in the measurement, you know that the function is balanced. So this is essentially the whole algorithm, and the point is that this UF is used only once to solve the problem. Now we can compare it to the classical situation. There are 2 raised to n possibilities. For x, and you want to find out whether it is constant or balanced. If you want a deterministic answer, then you have to just scan all the values until you find that it repeats or it doesn't repeat. And the guaranteed answer, you need to go through at least half of the list, because you may be unlucky and the first half you check doesn't repeat, but the next one there might be a different result, and then you will need half the list plus one more to make sure that yes, I have a guaranteed answer. But that is not the only situation we should be worried about. We can ask the question, what if I don't want a guarantee? I'm happy with a high probability. That I will make some checks for x, and from that I will just guess that this is the type of the function, and ask how much is the effort required. So this is the result, which is true in general, that if I want only a probabilistic result, I can get away with doing less work. And in practice, this probabilistic framework is the one which appears in essentially all applications, because even if the problems have a mathematical solution which is kind of precise, the real world, we don't wait for getting all the accuracy that is theoretically possible. As soon as you have reasonably safe probability, you just go ahead and use that answer. And this is true not only in statistical physics, but much more in biological context. You never wait all the way till you have a guarantee. As soon as you are reasonably confident, you just take up and finish the job. Sometimes you will fail, but that is not very common, and the world works like that. So we need to estimate that when will this thing go wrong. Okay, suppose I will measure x, not this huge number of times, but just some finite number k. And after that, I'm just going to guess what the nature of the function is. And then the probability will be related to how large this value is. So let us calculate. Okay. So suppose I measure one object. It can be any of the two possibilities, or even if it is a balance function, you don't know in which class it is going to be. So one measurement gives no information. You measure a second time, then you can say that the first measurement and second measurement give the same answer, or they give different answer. And in case of constant function, it gives the same answer. In case of a balance function, it will depend whether you pick the correct set or the opposite set, because it is half the time it is on one side, half the time it is on another side. So the failure is a function is balanced, but all k measurements if at any time the two measurements are coming out different, I know for sure that the function is balanced and the problem is solved. But this can happen that the function is balanced, but the measurements keep on giving the same result. You don't have to go all the way up to there, but at least it can happen a few times. And what is this probability? That you measured k times. First one did not give you any information. The second time you had two parts, but you by some chance picked up the result in the same part. So you have no information. Same thing third time, etc., etc. So it has a probability is some number. P is equal to 2 raised to minus k minus 1. It's a basically, first one doesn't contribute, but the second one has probability half of being in one set versus other. The third one, the same kind of thing. And function is balanced. That means every time you are going to pick up a factor of half for it being in the same part, and that produces this particular probability as a result. So this is the probability of getting a wrong answer, but now we have to normalize it. So for that, we make some assumptions. So let me assume, okay, that constant and balanced parts are some function is given and we don't have any result, so there is some fx, then there are two possibilities which I have make equal, so half the time it is constant and half the time is balanced, and in this case I will always have all the k measurements giving the same result. Okay, so there is no problem. Here the probability of all k results being the same is
how do you know that if you pick up random x and probability of it being a constant, it will reflect that fx will be constant, it is half.
if this is constant, whatever you do, results are going to come out to be the same.
Yes.
In this case, function is balanced, but you are unlucky and you can get with some probability all the results coming out same, even if the function is balanced. That is the probability I calculated. So what is the normalization? Well, I have to take the probability of this particular failure and divide it by the total probability that all the k results are the same. So that is equal to basically half is coming from here and this is p, so 2 raised to minus k minus 1 divided by half which comes from here, and another is the second term, and you can simplify this to give the result which looks like that. The point is these numbers are going to be very different than this particular result, and let me now give a label for this thing is norm. The probability of failure which I see all the functions came out to be the same and I'm getting still a wrong result. Let me call this epsilon. So what is the dependence on k on epsilon? And that you can take a log with respect to 2 and assume that k is large, etc. So it's essentially 1 over epsilon is equal to 2 raised to k, which produces that if you are given some value of epsilon, which is your tolerance for the failure, I want to make it 1 part in a million or something like that, very small number. What is the trials I should take? It depends logarithmically on epsilon. And the log is an important feature, but more importantly, doesn't depend on the input size. Remember this. These are an exponential dependence on n. This thing become independent of n. It just depends on what is the probability of failure you can tolerate.
For practical purpose, our assumption, if valid or not, constant and balanced parts are equally probable. This is our assumption.
Yeah.
So it is valid in practical situations.
The problem is defined in a particular way. You are given some values and you don't even know what the function is. It's just a hypothetical construction. You assume some value, but even if you make this thing unequal, okay, the probabilities, some constant factor will change, but this dependence is not going to change. And this is a drastic difference, which is why I said that probabilistic result needs less resources. Guaranteed answer may be a different story, but most of the time you are happy with probabilistic result. In quantum algorithms, it will be generic. Everything will come out with certain probabilities, and results can be very different. So here you need an exponential dependence. Here it is just a constant dependence. So what did you gain? Well, k is the number of times you ran the algorithm, and here it was used only once. So what you are gaining is essentially this factor of k, which depends on the confidence level which you want the answer to be. So this is an algorithm, well, somewhat artificial, and you can do an analysis. You can see there is some advantage. You can analyze even the probabilistic case and find that yes, you have some advantage. Can you make it concrete to some problem which is more common in mathematics, and that requires that this function which we stuck in by hand, we have to give it some particular form. Choose some particular function. It may not have the same detailed analysis, but ask the question that can you figure out the advantage where it is more tangible in terms of application. And that was done by these two people. Bernstein and Vazirani. So they chose a specific function which was a binary dot product between variable x and some constant a. And the task is find a. So this becomes similar to solving the problem of simultaneous equations. You are allowed to run this algorithm with different values of x, and so you will get a dot x1, a dot x2, a dot x3, and when you run the algorithm you will get on the other side 0 or 1. Remember, this is all done in binary language, and so the dot product is evaluated in the modulo 2 addition. And you have some simultaneous equation, a dot x1 is equal to some value, either 0 or 1, a dot x2 is equal to again some value 0 or 1, and you have inserted specific values of x's, job is to find a, so it's exactly a problem of solving simultaneous equation. It's in a binary language, but that is also, this is a solution of simultaneous equation. And what will you do classically? Well, it's fairly obvious once you think about it. I have n unknowns, which are the n bits of A. Okay, A1, A2, it can all be 0, 1, 0, 1, etc. So what will I do? I will take x, where the first bit is equal to 1 and all the others are 0. And I measure the function, it will give me the first bit of A. Then I take an x which is only second bit is non-zero, all the others are 0. I measure it, I will get the second bit of A, and so on and so forth. So classically, bitwise choice for x gives bitwise values of A. And what is the effort? Effort is n evaluations of f of x. That's it. It's a completely deterministic thing. You just evaluated n choices one by one by putting in specific input x. And you can't do anything more than this.
The dot product is defined as addition modulo 2.
Yes.
Then suppose if we put the first bit of x as 1, then we get a0 as a0 bar.
If you put more than one component of x, you have to do the addition. And it can happen that it can either become 0 or 1, whatever it is.
So if we put only one bit as 1 in x, we get the
Corresponding bit of A.
directly. It's not a bar or something. Just
No. It's if x1, the first bit is 1, and all the other bits are 0, the dot product is equal to first bit of A. All the other stuff is 0. And now we ask, what happens in quantum case? So we are going to run this algorithm. Same thing, except that now I know what is f of x. Okay, I run the algorithm and I see what comes out. So So final result is this: 2 raised to minus n summation over x and y, both minus 1 raised to x dotted with y, then minus 1 raised to a dotted with x of y, and this other part is unchanged. The only thing which I did is put in an explicit form of what of f(x) is. And now I can combine these two factors. So this is just minus 1 raised to x dotted with a plus y. And now again I look at what this summation is going to do. If this plus and minus signs are going to alternate because there are all x and y are occurring, both probability in 0 and 1 have equal amplitude, then it's all going to cancel out. So the only place where it doesn't cancel is where a plus y equal to 0. Then y get fixed. It is it's binary addition that a plus y equal to 0 means a equal to y. And the remaining summation over x will produce 2 raised to n terms, which will cancel the normalization. So this result, it's actually one of the identities of normalization, which is, I can write it in many different ways. It's a Kronecker delta. The only term which survives is y equal to a, and then summation over x cancels this 2 raised to n, and if y is not equal to a, the sum is equal to 0. And well, that means this. You measure this final state, and actually this y I should not write summation over here. I'm only summing over x, and then if this is 0, then it will produce a Kronecker delta, and the second summation of y over delta will just give you the answer. Which term of the summation of y will come out, it will give the state which is a, and y is equal to a. So now it is a specific problem because simultaneous equations are something which you are familiar with in linear algebra problems, occur many times. And now you have an explicit evaluation of the advantage. Here I required n evaluation, here I required 1. It's not a big gap, but it is explicit. There is no uncertainty left in any case, and there is nothing more you can do by any probabilistic trick, etc., if you want to solve this equation. And yeah, the conclusion is that this one it's a polynomial advantage. That is linear, but okay, fine. Doesn't matter generically. In the class that the algorithm saved you something. How much you saved? Well, it's a polynomial in the number of initial variables. Okay. After this algorithm, all these things require separate efforts in the sense that even though it looks like just a gradual change, you change a little bit over here, over there, to think about how to cook up such situations, it took years in between for people to go from one level to the next. And
so can you explain why did you remove y from summation?
this is an identity.
Here also y had values y1, y2, y3.
It's a minus 1 raised to x. This factor is either 0 or 1. Okay. If it is 0, then you will get a result where a plus y is equal to 0, which is equivalent to writing it's equal to 1.
In above line. We will use this identity in above line.
You will insert it in this result, yes. But this is an identity just involving plus and minus ones. If a plus y is equal to 1, then half the time x will have dot product which is 0, other type which is 1, and the right hand side will become 0. Okay. So the next step was taken by Simon, and it seems like a gradual progression, but it really provided the breakthrough. Okay. And all he did was take a function which is n bit to n bit. Remember, the original Deutsch problem had a function which was 1 bit to 1 bit, and the job there was just checking whether it's a 1 to 1 or 2 to 1. This one extended it to n bit to 1 bit, in the sense that initial fx was defined on n bit, but the final answer was only 1 bit, it's either constant or balanced. And Simon took the next step that I will have a more general function which is n bit to n bit. But of course, arbitrary functions will not give you any clue about what to do, so you will choose some particular property of the function. And he was clever enough or rather knew enough of the binary arithmetic to find a nice possibility that the function is such that f of x is equal to f of x plus a. And job is find this a, and obviously you have to put a condition a is not equal to 0. Otherwise there is nothing in the problem. So what did this definition encode? And one can easily see that if I do it twice, it's a binary addition, it will cancel out. So the function is periodic. And what is A? A is nothing but half the period. So function is not specified, but you are told that it is periodic in this particular way. Okay, so this is what can be called as a, so the language which I have used earlier, that it is called a relativized problem, in the sense that you are not given the details of the function, but only some property of the function is known. Yeah. Because you want to come back to the original point. Oh, sorry, this is fine. If you do it twice, you will come back no matter what value you add. But this says that after adding a, you are coming back to itself. It's actually the period. Okay. Yeah. This will be true for any number added twice. So it's a relativized problem. So function unknown, but a property is known. So how will you go about tackling this problem? Well, first, let me look at a classical version. There are two raised to n possibilities of x. How will you check for the periodicity? Well, you have to evaluate at least for 2x, and you ask the question whether the two answers are same. or different. And you can go about doing the same strategy, that I will measure the function for k values of x, like here. How many pairs I can check for comparing whether any one of them repeats or not. If I k measurement, it is k times k minus 1 by 2. And I will compare all those pairs, and if any one of them is equal, my problem is solved, but it can be that none of them are equal. So k evaluations allow checking of k times k minus 1 by 2 pairs. And none of them come out, then I have no knowledge of A at all. Okay, because it's not that I can guess A, it's just that I have no knowledge of A at all. Here the guess was there because I was told that the function had only two values like constant or balance, etc. Here I can do so many checks, but if all of them fail, I have no possibility of what is A, and how many possibility of A are there? Well, 2 raised to n. That's a guessing probability is too small. Okay. So the result, so for A requires one of this pair comes out with the correct answer, and the possibilities I have to run through, there are well 2 raised to k, the maximum value of k is basically 2 raised to n, nothing more than that, but this is quadratic in k, so the evaluation is square root of this number. Because by that time I will succeed in finding a pair which works. Okay. One of the pair has to work, and I am using k evaluation, pairs are so many, and in general I have to make these checks comparable to this, so this is the number which comes out. That I don't need to check all of them, well, square root of them will be a reasonable choice for getting a success probability which is order 1. Okay.
By this we are comparing 2 to the power, we will be able to compare 2 to the power n pairs.
Yeah.
But that would not be necessary.
It's a probabilistic answer, but you need at least that much. A smaller number will not do. That is the point.
There is a chance we will fail.
There is a chance you will fail, yeah. There is a chance that even with this many things you will fail. But there is a reasonably good chance that it will work. It's probabilistic, but it's a lower bound. And the square root came because once you have evaluated k, you can make so many different pairs and keep on checking pairwise. One of them might work at some stage, that's all. You can work out the probability just well, you have to calculate some binomial distributions, but it can be detailed. But this is something which, so this result is not a deterministic result. It's still a probabilistic result, but good chance of success. So doesn't have to be 100%. But without that, if you don't do this, the probability will be just too small. Okay, so this is essentially the classical situation. Quantum situations, now I have to define an algorithm. And I'm going to use the same kind of tricks, not anything different, and see what happens. The advantage is I have put in some particular property of f of x. So I don't need that extra ancilla which was flipping the sign back and forth, but you can write it in many different ways, depending on the convenience. So I will define this function u of f, which I need. It takes the extra bit to the value of f of x. And this was a generic description which I used in reversible logic, that I can evaluate this thing by using a control operation. And because the the control operation can be repeated, and if f of x is given some nice value, you can undo it by a similar transformation. But this is a function which is given as a kind of unknown box. So I assume that this is provided instead of writing that ancilla stuff. It is a kind of equivalent. So what will I do? Well, I will start with the initial state. Same thing, which is 0 to the power n, transformed with this Hadamard operator to the power n to uh, 2 raised to minus n by 2, x equal to 0 to 2n minus 1, and I have to write this register. So the first step is just to construct this huge superposition over 2 raised to n possibility, which is Hadamard transformation acting on 0 allows me to do. And then I will apply this UF. So it will produce a state which is it writes the value of fx in this extra register, whatever it is. And that is all I am going to do, nothing more than that. And that still is in this category that UF is used only once. Okay. And now I perform a measure, but not this state, but measure the ancilla. So it will give some value, I don't know what. So let me call that y, just to avoid confusion. This register had all fx sitting inside it. I measured it. I got some value f of y. I don't particularly care about that value, but I want to now see what happened to the particular state. And that means there are many possibilities over here. Measurement is projective, it projected on some answer, and what is the coefficient in front. So this coefficient in front will be all the components which have the same value f of y. So that is the part I have not measured. But what are those two components? Well, I am given this particular property, two components will survive. Because I have measured this, the remaining part is remaining unknown. So the result will be, well, I'll normalize it. It's a probabilistic measurement, whatever it is, but it will give me y and y plus a and that is the point, this getting this superposition out, which only the term which satisfies the periodicity is the important step. So some things different from the original scheme, but the ingredients are the same. I created a superposition, I used it to create the function evaluation and then projected it, so I got this particular state out. But I have to find out A out of it. This is a superposition of these two values. I can't just directly measure and find A from it. So I need some other trick, and the trick is essentially the same. So apply these two states came out of the measurement. I will apply this Hadamard operator on it.
Can you do superposition without doing A? We are doing superposition after F.
Because I measured F, I did not do anything to its coefficient.
So we don't know A.
You don't know A.
So how are we doing the superposition?
You don't know A, but this is a quantum state. because I fix this particular part, and when I do a projection, everything which is consistent with that projection remains. And everything which is orthogonal gets deleted from the quantum state. That is the axiom of quantum theory. So I measured this thing completely. It gave me some value, but I did not do anything of this register, so everything which is consistent with that particular value will remain there. And there are two values in this particular case. So what is going to happen? This h raised to n times 1 by root 2 is there. Y. This is an ordinary superposition, but inside the argument is a binary addition. I leave around me. I don't particularly care what it produces. That is an unknown part of the function. It doesn't matter. What happens if I apply this Hadamard transform to this? And you can quickly write down the result, which is 1 by root 2, then 2 raised to minus n by 2, sum over some variable, which I have to give some label. X and y I have already used, so I will use z. So let me try. And what did this allow me to do? Well, it was a summation over here, and y was unknown, so I could not have directly calculated a, but this allowed me to put the whole thing in an exponent. And then the factor which depends on y gets factored out. Okay, so this is minus 1 z y times 1 plus minus 1 and that's a important part. This is the trick which appears over and over again, and it's a general property of Fourier transform. You have a periodic function, you do a Fourier transform. That is what this object is doing for you, putting it in the exponent, and then the common thing can be factored out. Fourier transform does the same thing, that if you have some argument and you have produced this factor, it's not a binary product, it's e raised to I, x, y, whatever it is, but it puts it in the exponent, will allow you to factor out the stuff. And now this thing doesn't depend on this variable which was a superposition of all arguments. And so I can rewrite this thing is, this thing is going to occur twice. So the 1 by root 2 can be that the summation which was over 2 raised to n minus 1 possibilities is now restricted. It is non-zero only if z dot a equal to 0. Otherwise, the other terms drop out. No, it's not equal to a, it's just z dot a equal to 0. Every value of z which satisfies this constraint will survive. How many values are there? So, terms, number of terms rather, with whatever the total number divided by 2. It's a linear constraint. In a space, you can choose a particular axis. For example, for A, let it be along the first component. That means z1 will become equal to 0, and all the z2 to n minus 1, they are arbitrary. You can count it any different way you want, but one constraint is there. There are so many different terms which remain. But the point is that this number is smaller than the original one by a factor of 2, and which is the consequence of this particular constraint. So that now gives you a way to solve the problem, because what I will do is measurement of whatever the z gives values satisfying this particular constraint. There are still a huge number of terms. So when I try this measurement, there are 2 raised to n minus 1 different possibilities. But the point is, each one of them will satisfy z dot equal to 0. And what is this? It's a bunch of linear equations, simultaneous equations. There are n variables. If I generate n independent equations, I can solve them. Okay. Well, there is one constraint. There is a trivial solution which is a equal to 0. That I kind of removed it because then the problem is non-existent. So a not equal to 0 means I need n minus 1 independent simultaneous linear equations for solution. And that is the crux of the matter. The number of possibilities is huge, but the number of independent equations I need is only n minus 1. It's not exponential. And so I will just run the algorithm till I get a bunch of independent equations, and then find whatever is A.
How long?
Yeah, so it can happen that when I perform measurement I can get some set of equations, but the next one is dependent on the previous one. But the probability of that can be made arbitrarily small. You have to do some counting of that type with binomial possibility. The reason being that the gap between n and 2 raised to n is very large. Okay. So there will be some dependent combinations inside them, but I only need n minus 1 independent, so there will be some overhead. So how many trials you need? With say n plus k measurements of z, this can be achieved, and what is the extra work you have to do? Well, you need to do some calculation which I am not going to work out in great detail, but the behavior will come out like this. It is just going to be log 1 over epsilon. So you have some overhead which depends on the confidence level you want, but it is something which is independent of n. It's a counting argument one can do. It's similar to this, but that is the result, and that means you have solved the problem. You found the periodicity of the function. You have used the Fourier transform in a disguised manner. And what is the difference in the effort? Exponential in n, linear in n. And this was a kind of guaranteed proof. That this bounded error quantum polynomial proof in a relativized problem, which I mentioned earlier. This inequality comes precisely because one of them, this one is exponential and this one is a polynomial. That is how the complexity classes were defined, by something which is polynomial on one side and anything bigger than a polynomial on the other side. And that on ingredients I mentioned, one is a periodicity and the other is a Fourier transform. So this was literally a breakthrough in terms of algorithm development. So now some bit of history. What happened? Simon worked out all those things and submitted the paper to a conference, Foundations of Algorithms, whatever, FOCS, Foundations of Computer Science kind of situation. And the paper got rejected because nobody thought it was anything interesting. And by some coincidence, Peter Shore was on the evaluation committee of that paper. So yes, the paper got rejected, but he realized that there is something interesting in the paper. And he knew a very important problem where these two properties play a very important role. There is a periodicity problem which has been solved, and the technique which is used is a Fourier transform. So he went back, he took this periodicity problem and generalized not on this binary Boolean logic, but on a set of integers or real line or whatever you want to call it, where the one-dimensional systems are typically phrased. And he found a solution with the same property, that there is an exponential gap between the classical version and the quantum version. And what was the problem that he knew about where this periodicity plays an important role? That was a integer factorization problem. So that is the way Peter Shore landed up in this particular result. Of course, he knew that integer factorization had lots of application going in cryptography and all kind of things. And all he needed was that it's a periodicity problem. Again, he knew about it. He needed that the ingredient to solve it is Fourier transform. And he took it from this binary Fourier transform trick to a real line or set of integers Fourier transform, and things came out essentially in identical fashion. And that became a big breakthrough in the development of quantum algorithm, and Shore got many awards and prizes and all that kind of things. Of course, he did many other things as well, he didn't just stop at this particular problem, but that integer factorization problem is really what started this field on a very, exciting level. Until then, people were not paying too much attention to quantum algorithms. And that is the history, and the origin of the history is sitting in this particular problem. Simon finally got the credit for the problem. His paper was rejected, but then people realized that yes, the paper should have been given its own emphasis, and it got published later on, and now people give him credit for coming up with this particular idea. But that's the way things happened. So this is actually really the important development in case of algorithms, that yes, we started with very artificial thing with this Deutsch problem, 0, 1, etc. But step by step, we could take you to a stage where you can connect it to applications which are important. And all these problems are based on linear algebra. Fourier transform is also an operation in linear algebra. Simultaneous equations are also some applications in linear algebra. And you are just trying different ways to solve them and coming up with new kind of algorithms. So yes, I will stop here, and I will come to Shore's algorithm probably later in the course. It requires much more mathematics, not because of Fourier transform. Fourier transform part is identical to whatever I did over here, not too complicated. But connecting the factorization problem to the periodicity problem requires all kind of tricks, which are actually involves number theory, group theory, all those kind of ingredients. It's all classical, but you have to know about them so that you can make the connection and The final quantum advantage will be the same trick of Fourier transform, nothing more than that. But before I do that, I will do something else in between, something less mathematical, just to keep your mind relaxed before dumping all kind of mathematical stuff on you. And that I will do in the next few lectures.